All right. Now we consider some properties of the Laplace transform. The first property that we always like to speak about is the linearity. We have been only dealing with linear transforms throughout this course. So, the first property of linearity is pretty obvious. It simply says that if you have x1t going to x1s, x2t going to x2s, this with an ROC R1 and this with an ROC R2, then xt equals x1t plus x2t will go to xs equal to x1 x1s plus x2s, that normally should have an ROC that's equal to R1 intersection R2. But there can be peculiar situations where cancellation of poles and zeros will lead to an ROC that is greater than this. So, the more general answer to this is not this, but to say that the overall ROC will contain R1 intersection R2. It might have more points than R1 intersection R2 sometimes. As an example, we will consider the following. Suppose we have x1t equals 1 by s plus 1, x2 s rather x1 omega x1s equal to 1 by s plus 1, and x2s is equal to 1 by s plus 1 times s plus 2. Let us say this one has an ROC sigma greater than minus 1, this has an ROC sigma greater than minus 2, right. Now, if R was R1 intersection R2, we should get R as sigma greater than minus 1. But let us see what we get. What is XS? Let XS be given by x1s minus x2s, which is equal to 1 by s plus 1 minus 1 by s plus 1 times s plus 2. Then XS equals with a numerator of s plus 2 minus 1, which equals s plus 1 over s plus 1 times s plus 2, which amounts to 1 by s plus 2. Now, given that both the input signals have rightward ROCs, they both represent right-sided functions, and hence one expects x of s, which is the difference of two right-sided functions, to be also right-sided. Hence, we will say, we can see from this that the ROC of this must be sigma greater than minus 2. This surprises us because if R had been equal to R1 intersection R2, we would have got the intersection of sigma greater than minus 1 and the intersection and sigma greater than minus 2 would simply be sigma greater than minus 1, but what we are actually getting is this sigma greater than minus 2, which is more than the intersection of the two ROCs, and that has evidently happened because of the fortuitous cancellation of this with this, which has knocked off a pole to the right of the s equal to minus 2 pole. It is this that has expanded the ROC. I presented this example to show you that these things can happen, and that is why we say that the ROC is simply for the sum of two expressions is given by R superset of R1 intersection R2. Now, let us move on to some other properties quickly. Time shift. If xt has a Fourier transform, Laplace transform xs with an ROC of R, then x t minus t naught will have a Laplace transform of xs e to the power minus s t naught. The way you prove this is exactly the same way that we did for the continuous time Fourier transform. The steps are pretty much the same. We only have to worry about the ROC. Now, what can we say about the ROC here? You see, xs is known to converge over region R of the S plane, that is a set of points R on the S plane at which xs is finite. Now, we are multiplying xs by e to the minus s t naught. Now, e to the minus s t naught for any finite s is a finite number, and so if xs is already finite, then e to the minus s t naught xs will also be finite. If xs is not finite, then e to the minus s t naught times xs will also not be finite. In short, multiplication by a finite valued function such as e to the minus s t naught will not at all affect the ROC. So, this still has an ROC equal to R. Next, frequency domain shift. We can consider this under the same number. So, let us say frequency shift. What we want to ask is, what is the Fourier transform of x? What is the time function corresponding to x s minus s naught for some s naught? Now, again, following the usual steps, you will find that this yields e to the s naught t x t. This yields e to the x naught t s t. Next thing we have to ask is, what is the ROC of this? Now, all that has happened to the ROC is, it has got, the entire function has got shifted by an amount s naught. X of s is now shifted to x of s minus s naught, and hence what will happen is that every point in the ROC that was there earlier will get also correspondingly shifted. So, if R was the original ROC, if R was the original ROC as we have written over here, then the new ROC, which I will call R dash, is just equal to R plus sigma naught, where S naught equals sigma naught plus j omega naught. So, the new ROC is obtained by shifting all the old ROC points by the amount sigma naught. Next property, time scale of xt. Time scale of xt. So, if xt has a Laplace transform xs with a region R, what will happen to x at? Going by a process similar to what we used for the continuous time Fourier transform, we will get a very similar expression 1 by mod A x of s by A. Now, what is the ROC of x of s by A? It turns out that, again look at the expression, x of s by A is what we now have. Earlier we had x of s with a region of points R. Now, x of s by A will simply yield a new set of points which relates to the old set of points by the following means. So, you take R dash equals the set of points sigma plus j omega by sigma by A plus j omega, where sigma plus j omega was in R. Next, we speak of convolution. Along lines very similar to what we have earlier followed, it turns out that x1 t convolved with x2 t will have a Laplace transform given by x1 s times x2 s, where the ROC R of the convolution will contain R1 intersection R2. It should normally be equal to the intersection of R1 and R2, but it could exceed it for reasons similar to what happened with the discussion of linearity, that is the cancellation of some poles of x1 with the zeros of x2 or vice versa. This would free up the ROC a little and you could have an ROC larger than before. Next, we consider differentiation in time. We have the inverse Fourier transform expression that we had, inverse Laplace transform expression that we had already obtained, and that was that xt was 1 by 2 pi j integral over a vertical line lying in the ROC s equal to sigma minus j infinity to sigma plus j infinity of x s e to the st ds. This is what we have. Now, if we differentiate this against time, the only thing that gets differentiated is e to the st. So, you just get s xs as the answer. That is to say that d by dt of xt will have a Laplace transform xs. Now, what do we expect to be the ROC of the new function if xs had an ROC of r? What would be the ROC of sxs? We see that there is a factor s that multiplies xs. Now, factor s is known to be finite for all the finite s plane. So, if xs is finite in some place, sxs will be finite in that place. If xs is not convergent at some place, then nor will be sxs. So, on this argument we can say that the ROC of sxs must be the same as the ROC of xs, except for the usual proviso that if there is a pole at s, that is a pole at the origin in the expression for xs, then that pole will cancel with s that has now appeared as a factor over here, and the result will be an expansion of the ROC. So, we can only say that R dash is a superset of R. The new ROC is a superset of R, probably the same, but if XS has a pole at S equal to 0, then it will, that pole will cancel with the factor S that has just appeared, and you will have an expansion of the ROC. Next case, differentiation in frequency. That is, we want to ask what happens if you consider d XS by ds. This turns out to have a time function counterpart given by minus jt minus txt, there is no j, minus t xt, that is all. Okay. Now, the question is, what is the ROC of this? If XS had an ROC of R, then what is the ROC of dXS by ds, which transforms to minus t xt. In order to determine this, we have to argue along slightly different lines. We have to argue in terms of the time domain function xt and not with respect to the Laplace transform as we have been doing up to now. There, as for example with differentiation in time, we looked at the ROC of XS and said that if a point lies in the ROC of XS, then SXS will also lie in the ROC, that is, that point, the same point will also lie in the ROC of SXS. Now, we look at the time function. Now, the argument is this: we are looking at points sigma plus j omega in the S plane, for which x t e to the minus sigma t is absolutely integrable. So, the fact that at some point sigma, let at some point sigma plus j omega, let us say sigma naught plus j omega naught equal to S naught, x t e to the minus sigma t be a I, be absolutely integrable. Then we have to ask if at that same point will at S naught t x t, or if you like minus t x t e to the minus sigma t be a I or not. That is what we have to ask, and the answer is very straightforward. You know that t, the new factor in the time function, increases linearly with time, whereas e to the minus sigma t attenuates exponentially. And so, if you have an outright war between something like t and e to the minus sigma t, e to the minus sigma t will win hands down. In short, we can be certain that if for any sigma e to the minus sigma t x t converges, that is absolutely integrable, then so also will minus t x t e to the minus sigma t. There is no problem there. Furthermore, we can say that even if instead of t you had t squared or t cubed or t to the power n, even those when multiplied by x t and e to the minus sigma t would still be absolutely integrable. In short, differentiation one time in frequency or more than one time in frequency does not bother the ROC. The ROC will remain unchanged. ROC will remain unchanged. Fine. Next, let us consider the running integral, the Laplace transform of the running integral of x t. Let x t transform to x s with an ROC R. What happens to integral minus infinity to t x t dash dt dash, which is the running integral? Well, in order to answer this, let us recall that this simply equals ut convolved with x t. This is an old result which we have been carrying around for a while. So, if you want to answer this, we already have a theorem on convolution. So, we are ready to use it, except that we do not know the Laplace transform of ut. So, what is the LT of ut? Well, ut is nothing but a special case of e to the minus a t u t with a equal to 0. Thus, instead of 1 by s plus a, we get ut transforming to 1 by s. Just put a equal to 0. So, ut transforms to 1 by s with an ROC of sigma greater than 0, because this the pole here 1 by s has a pole at the origin. So, sigma greater than 0 is the ROC. So, this is what we know about ut. US you can call it now, because it is the Laplace transform. So, now we say that integral minus infinity to t x t dash dt dash equals ut convolved with x t, which is equal to which is not equal to, but which transforms to 1 by s times x s. Now, what is the ROC? The ROC is the intersection of the ROC of x s with the right half of the s plane, which is the ROC for this. So, r dash equals r, because x had a Laplace transform with an ROC of r intersection the set sigma plus j omega for sigma greater than 0. That is the ROC of the running integral, and that gives you the expression for the Laplace transform of the running integral. This completes most of the important properties of the Laplace transform. In fact, we have come to the close of the Laplace transform as a topic for discussion at the level of this course. I will now conclude with a few final remarks. The Laplace transform is a very powerful means of understanding the behavior of signals. More importantly, it gives us powerful tools to discuss the stability of systems, for which we can take the Laplace transform of the impulse responses. Now, let us understand a few things. Let x t have a Laplace transform, then will it have a Fourier transform? Continuous time Fourier transform. How do we answer this question? To answer this, we will say, look at the ROC if S equal to 0 plus j omega, which is the what you call the j omega axis, is in the ROC, then xt has a Fourier transform, because on the j omega axis we are simply evaluating the of xt e to the minus 0t, that is sigma equal to 0, which is simply equal to xt. That means that whenever the imaginary axis lies within the region of convergence, clearly xt will have a Fourier transform. Now, if next step, this is the first step of the argument, the second step of the argument, if xt has a Fourier transform, that means that xt is absolutely integrable. Okay. Finally, we derived long ago a condition for stability for the stability of an LTI system with impulse response HT. The condition was absolute integrability. Putting all these 3 points together, we conclude the following: if Hs is the transfer function for the impulse response HT of an LTI system, then the system is stable if the ROC contains the j omega axis in H of S, well, j omega axis. Further, next argument, the ROC contains no poles. We are just recalling the argument. Recall the ROC contains no poles. right. Now, there are only a few possibilities for the ROC. The ROC we found can either be leftward, or it can be rightward, or it can be everywhere on the S plane, or it can be in the form of a narrow patch. These are the only 4 things that can result by intersections of elementary ROCs. All over the plane. This is possibility number 1. The second possibility is leftward. Third possibility is rightward. And the fourth possibility is vertical band. Of finite width. These are the only 4 possibilities we have. Now, if the system we are concerned with is causal, HT is right sided. And the ROC will be rightward. Assuming it exists, of course. Is rightward. If a rightward ROC contains the j omega axis, then all its poles refer to point number 4 just given above. All its poles must be in the left half of the S plane. Summary. A causal stable LTI system will have all its poles in the left half of the S plane. No poles in the right half. That's the summary, that's the conclusion of all the arguments. Maybe I should call it conclusion. And Along exactly similar lines, if one argued for anti-causal systems, anti-causal stable LTI systems will have, I do not need to go through a very symmetrical set of arguments once again, all poles in the right half of the S plane, no poles in the left half. So, these are pretty advanced conclusions that one can come to about the pole and zero placements, pole placements in particular of LTI systems which are stable.